Hello, I'm Professor Steve Miller. Today we'll be looking at the combination of Fanno flow and Rayleigh flow. Then we'll look at the Prandtl number and Reynolds analogy. These come out of the analysis. Then we'll look at isothermal flow and a particular example. The isothermal flow, of course, is where the temperature is relatively constant in a Rayleigh-Fanno flow. Let's look at some analysis. We note that there's a whole class of problems where the order of frictional effects and heat transfer are on the same order. And these do come up in engineering problems, and we'll look at the mathematics behind this, as I just mentioned. Before going through this class, I recommend reviewing Fanno flow and Rayleigh flow and their graphical solution approach first. Here's a diagram of how we'll analyze the problem. Note I've taken this from another source, and V is really U. But nonetheless, in the control volume in a pipe, which goes from left to right, we'll draw a control volume as the dashed lines. And there's a shear stress tau sub W, and there's some heat transfer noted by Q, a delta Q dot, a finite rate of heat transfer. The flow moves left to right, and we have a state 1 of U, rho, P, and T for velocity, density, pressure, and temperature, stagnation, respectively. At the end of the differential control volume with length dx, we'll have an increase of quantities du, d rho, dp, and a change in the total temperature, which goes back to isentropic flow, which we talked about a number of classes ago. Let's now look at some analysis. We can immediately write the conservation of mass. d rho over rho plus du over u is 0, which we've showed in previous classes. We can also write the equation for momentum. dp plus a half of rho u squared f dx over d, where d is the cross-section or equivalent cross-section of this stream tube, and f is a frictional factor, plus rho u du is 0. We note the definition of Mach number is U over the square root of gamma RT as shown previously. Gamma is the ratio of specific heats, R is gas constant, T is static temperature, M is Mach number, and U, of course, is velocity in the streamwise direction. We can differentiate this quantity and find du over U is dm over m plus a half dt over t. Combining these two equations, we can now show equation 666 of this slide deck. You'll see it's a function of differentials of pressures and temperatures and Mach numbers with the frictional effect and diameter. We haven't accounted for energy. Since it's a compressible flow, it's essential. And we'll write a concise energy equation. The change in heat transfer will go as C sub P, specific heat and constant pressure, times d dt naught, which of course is stagnation temperature. We can then look at isentropics. Remember the isentropic equation. T naught goes as the static temperature times 1 plus gamma minus 1 over 2m squared. We can now combine these equations, 668 and 667, and come up with 669. That is, we'll take T naught and replace it, and then solve for delta Q over CPT. We have the equation here with differential dm. Now recall, for perfect gases, we have the ideal gas law, which is the fourth equation we'll examine. We have conservation of mass, momentum, energy, and conservation of ideal gas. We can then combine these expressions together and find a different form of the continuity equation in 671. We have dp over p of negative du over u plus dt over t. We can now combine these equations with the definition of Mach number, and indeed we retain dp over p of negative dm over m plus a half dt over t. We've already found this equations for dp over p and dt over t, and we can substitute in 672 and find the equation at the bottom of this slide deck, which is really one equation, and this has been mistyped. We'll just call it 673. I have an equation for, of course, heat transfer, Mach number, frictional effect, and diameter is equal to only a function of Mach number in its differential element. We can rewrite this and simplify it in a better form. Now we have an equation for Mach number given a particular change in heat transfer and an initial stagnation temperature, where Cp is a constant, when F and D are frictional effect and diameter. So we seek to try and solve this type of equation. And note, we've made no assumption about cross-sectional area being constant like we have in previous lectures. Now, analyzing this equation, we can introduce, finally, the recovery factor for these types of flows, which will be introduced again later in the class when we talk about high-speed boundary layers and hypersonics. We see that this equation shows how heat addition and frictional effects are indeed related. And we can try and express the heat transfer change in terms of a mean convection heat transfer, H bar. Now for compressible flows, which are the ones we study here in this class, we'll see that there's a heat transfer between the area, equivalent area or differential area of dA sub P is pi d dx, where d is the diameter and a is the area of a circular stream tube. And we can rewrite this as 676. This is very much like your typical relation between Q and temperature and Cp, as we showed in a previous equation, which is equation 667 of this slide deck. After we make that substitution, we'll introduce some variables. Here, we've rewritten T as Tw, which is the duct wall temperature, and Taw, which is the adiabatic wall temperature. Now, we'll have to account for viscous effects, which makes the process irreversible, and we won't be able to recover the particular temperature, that is, making the recovery of temperature impossible through the flow. And we'll define the recovery factor, the temperature at the wall minus the static temperature divided by the stagnation temperature minus the static temperature. Remember, stagnation temperature is from isentropics, and Taw we introduced in the previous slide as adiabatic wall temperature. Now remember the stagnation quantity for T0, which we already introduced. Combining 667 with the definition of the isentropic total temperature, we can write the adiabatic wall temperature again with R. And we'll have 2 plus R of gamma minus 1 of m squared all over 2 plus gamma minus 1 m squared times the stagnation temperature at the beginning of the particular differential element. This is a recovery factor, and now it'll allow us to finally introduce the idea of the Prandtl number. And we'll see Prandtl number varies between laminar and turbulent flow in these particular cases. Laminar flow, we'll see the recovery factor goes as the Prandtl number to the half power, and for turbulent flow, the recovery factor will go as Prandtl number to the third power. We'll see indeed that the Prandtl number is a non-dimensional parameter, not unlike Mach number or Reynolds number. In words, it's the product of the specific heat at constant pressure Cp and the dynamic viscosity of the gas mu divided by the thermal conductivity K. Here it is as equation. The Prandtl number is defined as Cp times mu, that's viscosity, divided by thermal conductivity. It can also be written as the ratio of kinematic viscosity to the thermal diffusivity. We might write PR equals kinematic viscosity divided by alpha, where alpha is the thermal diffusivity, which goes as the thermal conductivity divided by the static density. Now we find that indeed Prandtl number of gases is generally close to unity, but I'd like to note that generally for laminar flows, most people will set PR to be about 0.70, and for turbulent flows, they might set it to be something close to 0.92 or 0.90 in that range, depending on the flow and the preference. So both these quantities are close to unity, and in this analysis, we'll just assume that it's very much close to unity. So we can go back to our previous equations for heat transfer with the temperature change between the wall and stagnation temperature with the averaged heat transfer. And so for these gases, we can write 679. This gives us a relation between the mean convective heat transfer coefficient and the frictional factor. And this is what's called Reynolds analogy, which is this relation. Now for Prandtl numbers, especially for turbulent flows, we might assume that they're close to unity, and then we can write h bar as rho u Cpf over 8. And then we've closed this problem to find an average heat transfer coefficient with the frictional factor Cp and momentum per unit volume of the flow divided by the factor of 8. Now, if we make a constant area assumption, things become simpler, and we still would be able to solve the previous equation which we developed without a constant area assumption if we knew the differential area, or area as a function of x. Here we'll just say area is a constant once again, which simplifies our problem, and rho u, of course, may be defined in any other particular equation, or excuse me, defined anywhere in the flow as a constant. Making this assumption, we'll find 681, and we find a simpler equation. You'll see it only involves m, dm dx, m as itself on the right-hand side, gamma, the ratio of specific heats, the change in total temperature with respect to x, and of course the frictional factor, which we'll consider to be a constant. And so if one knows d and f as constants and the variation of the total temperature, then we might be able to solve this equation through a simple numerical integration. So numerical solutions are absolutely essential and possible for these types of problems. And it's very hard to find nice, simple graphical solutions like we did previously, but we'll still propose a type of approach. One might categorize these problems in two types. One is where there's a constant wall temperature, and the second is where there's a constant heat rate, that is, Q is a constant. So we either have T equals constant or Q is a constant. And in words, we've given some examples of where this analysis might apply in actual problems. Let's look at the first case where we need to determine, of course, T as a function of X. So of course, the temperature in the flow is a little bit different than the wall temperature. Remember, wall temperature is denoted by T sub W, which in this case is a constant. Making the constant area assumption and using TW equals a constant, we simplify our equation 682 to 684, which you're welcome to try yourself. This makes a much easier integration. And through integration simplification, and assuming an exponential distribution of the stagnation temperature, we'll find equation 685, which of course is much simpler. And you can see this exponential distribution through the factors e to the 2f, f 2dx. And so this equation can easily be solved through integration of both sides with respect to x and knowing the conditions at the start and exit of our pipe flow in distance L. If we consider a constant heat rate problem, that is, some Q is constant along the duct, then our equations, just like the previous slide on 1031, will be reduced in 1032 through equation 686 to 688. It's the same type of assumptions. Here we introduce a simple factor beta. So 688 would be, of course, for constant heat rate into the flow. Compare 688 with the assumed form of an exponential temperature distribution of 685. I would like to note that you can also choose other distributions, and the exponential one might be the simplest to produce one of the simplest forms of a possible solution. But any type of distribution could be used, but this one, of course, is just chosen to simplify the problem for illustrative purposes. If you use these types of flows, just like in Rayleigh and Fanno flow, you can find all other properties once you've done the main integration problem numerically. I've summarized these equations for changes in temperature from point J to K, for stagnation pressure, for density, and for change in entropy. You'll see the entropy equation is, of course, assuming gas law, like we had discussed and derived in one of our beginning classes. You'll also see that, of course, these have changing areas. And so you're able to account, if you know the Mach number at the beginning and end of your flow with a Rayleigh-Fanno flow, with changing areas, the ability to calculate all other thermodynamic and stagnation quantities with closed form equations. If we assume that the flow is isothermal, that means that the temperature through the whole flow remains constant. This is the so-called isothermal Rayleigh-Fanno flow, which simplifies our previous equations greatly. These two happen occasionally. It is a major misconception to regard the isothermal flow as one that not requires any energy exchange. Indeed, it's a balance of energy exchange with the frictional effects that balances the temperature in the flow. And these can, of course, be found in engineering problems. Let's analyze an isothermal flow. Once again, we'll start with the continuity, momentum, and energy equations, which we've written on this slide. And these are very much similar to the previous ones. For example, d rho over rho plus du over u is 0. It's a steady conservation of mass equation. The same happens for 695. We have pressure, a momentum term, the friction in the numerator and diameter in the denominator is balanced to 0. Here's a diagram of our problem. It's very much exactly the same as the last one. We can then look at the momentum equation and rewrite it as 697. We can then rewrite the differential momentum equation as 697. If we look at the energy equation and divide by the mass flow rate, which we know is constant at every cross-sectional area because we assumed it's a steady one-dimensional flow, we'll find this new form here, that delta Q dot over m dot, where m dot is constant, as I noted, equals Cp dt naught, where T naught is the stagnation temperature. We also recall that this perfect gas law can be expressed in the differential form between pressure, density, and temperature. We have assumed that the static temperature within the flow is constant, and therefore, on the last term in 699, dt over T should be 0 because dt is 0. Temperature is a positive scalar. We can then write dP over P equals d rho over rho, and so we find closed form expression between the differential pressure and density. We also remember and recall that m equals u over c, or a. That's the local speed of sound, which is the square root of gamma r of the static temperature. So really, since static temperature is constant, the Mach number is only a function of u, and also the speed of sound is constant. We can do logarithmic differentiation of this particular term now and look at dm over m is du over u. We now have terms du over u, d rho over rho, and we can put them in combination of equations, and we'll find dp over p equals negative dm over m. We can then rewrite 702 as 703. dm over m equals gamma m squared over 2 all over 1 minus gamma m squared by relating differential pressure and pressure to our momentum equation. Here we'll see that this shows that there's some particular so-called critical Mach number for isothermal flows. And you'll see that indeed, if you have gamma m squared equals 1 in the denominator of 703, then you'll have a singularity, a critical Mach number. Let's explore what that means physically. Now, if m equals 1 over the square root of gamma, and for gamma 1.4, for say air, it'll turn out to be a value of about 0.8452, which is a subsonic high-speed Mach number. That's indeed the critical Mach number where the singularity happens. Now, if Mach number is less than that value of 1 over the square root of gamma, then this flow will be called subcritical, and it indicates that the Mach number will increase with x. This is just like the previous flows for Rayleigh flow and Fanno flow, that the Mach number is generally increasing with friction or heat addition for subsonic flows. But in this case, the critical value is 0.8452 for gamma 1.4, unlike the just purely Rayleigh and Fanno flows where the critical Mach number is 1. If our Mach number is greater than 1 over square root of gamma, then we'll have a supercritical flow, and of course m will decrease with x. This is rather intuitive once you learn Rayleigh and Fanno flow, of course. Now, the frictional effects, of course, need to be balanced by the heat transfer to maintain isothermal flow. And one might ask, what is that particular value? Well, we've shown this particular equation in 704. We see that some change in the heat transfer into the flow will go as Cp dt naught, will go as Cp T naught gamma minus 1 m4 over gamma over 2, all over 1 plus gamma minus 1 over 2 m squared times 1 minus gamma m squared times f dx over d. Now, as Mach number approaches 1 over square root of gamma, Q, of course, will go to infinity because of the singularity. And you can see this in this equation. This means that there'll be an infinite need for heat transfer to maintain an isothermal flow near the critical Mach number. Of course, this is naturally impossible to have such a high amount of energy transfer into the flow. And the flow would accelerate in a constant area duct from low Mach number to m equals 1 over square root of gamma. And these set of equations would break down at that Mach number or very near it. This assumption of isothermal flow is absolutely valid and can be seen in cases and realized physically for small velocity, low Mach number flows. It is often desirable to obtain an expression for pressure drop and Mach number variation as a function of x, just like we did for the general case of Rayleigh-Fanno flow, which we showed a few slides ago. And we'll show quickly how to do this here. We'll integrate our equations just like we did in a Fanno flow or Rayleigh flow equation and solution approach. I've summarized this in equation 705, 706, and you can isolate FL over D and perform the integration analytically. If you substitute M1, M2 on the right-hand side, you'll get 707 from the limits of integration. You'll have F over D is only a function of M1 and M2 and gamma. We have previously showed ratios of TO1 and TO2 if we simply write them as their respective isentropic quantities at M1 and M2. We can then integrate with the continuity equation and get equation 709. We'll get the inverse ratios of static pressure are ratios of Mach number with density and velocities. You'll see that there's now an equation for stagnation and static pressure ratios given in 710 through 711 with respect to Mach number. You can then, of course, make these substitution and write total pressures, PO1 and PO2, as a function of Mach number. We'll choose a reference state for a graphical solution or integration approach just like we did for Rayleigh and Fanno flow, except we'll set the critical or reference state to 1 over square root of gamma and note it as a star or the critical value, just like we did before. So in this class, we've had critical values so far of 0 or 1. And this is one of the first cases, which we'll see it as 1 over square root of gamma. We'll also see that later on in our supersonics section and transonics. We use the exact same solution approach that we used for Rayleigh flow and Fanno flow independently, and now we can find closed form equations for stagnation temperature and stagnation temperature with respect to the critical value. See, we replace 1 and drop the subscript and take in the subscript 2 and replace it with sup star. And now it's only a function of Mach number. That's the Mach number at a particular point in the flow. On upstream, that is, of where it becomes a critical value of 1 over square root of gamma. 714 then illustrates and finds all other quantities, that is, the starred or critical quantities with respect to a particular flow quantity upstream relative to the critical value. Summarizing and finalizing these equations, we'll have FL max over D of 1 minus gamma m squared over gamma m squared plus the natural log of square root of gamma m squared. So now we have, for isothermal flows, a closed form equation. These are very much like the tabulated formulas for Rayleigh flow and Fanno flow independently shown in the tables for this class. And the solution approach is exactly the same. Let's look at a quick example for isothermal flow to illustrate these concepts. Here we'll have methane and going through a gas pipeline, and it'll have a velocity of 15 meters per second and a static pressure of 500 kPa. Here the pipeline is 200 meters long and 8 centimeters in diameter. So we have an L and a D. L is 200 meters and D is 0.08 meters. The gas temperature we will hold at approximately 288 Kelvin, which is about room temperature, throughout the whole length of the pipe, which is 200 meters. And we're asked to find the static pressure drop. The gas will be methane, and it has a value of Cp over Cv, or gamma, of 1.32, and it has a particular molecular mass of 16, which you can look up online or a book of tables. And we'll assume that the frictional factor of this particular flow is 0.025. Let's look at the solution. First, we simply need the inlet Mach number. M1 is nothing but U1 over square root of gamma RT. We've given most of these properties already. Note that 8314 is the universal gas constant divided by 16. That's R, which is, of course, molecular mass. 288 is the temperature, gamma is 1.32, velocity is 15 meters per second initially. So the initial Mach number is very low, which absolutely gives us a valid solution for the isothermal flow problem. We get 0.033749. A lot of digits there. We can also immediately evaluate FL over D. We know F, we know L, and we know D. Plug in those values, we get 62.5. Now, just like Fanno flow or Rayleigh flow, we have worked hard and used the same simplification and solution procedure as Fanno flow for isothermal flow. We can then write the state of FL max over D at 2 equals the state of FL max over D at 1 minus the difference, which is simply FL over D, which we already know. We know state 1. We can look up L max based on the current properties. That's the distance of a fictitious pipe longer than the length of the actual pipe to, of course, bring the flow Mach number to the critical value. We can then solve for FL max over D at state 2. Plug in the values, we get 595.1265. Therefore, our Mach number at state 2, by plugging FL over D at 2 into our previous equation for Mach number and FL over D, we can solve for M2 and get 0.035459. We've already worked hard and used the same solution approach as Fanno flow for the ratios of static pressures and inverse ratio of Mach numbers. We know these values at state 1 and 2, and we can put in these values and get 0.9518. We can then easily solve for, of course, P2, and we'll find, or we can solve for the difference and then solve for P2 based on P1, or just the pressure drop if we knew P1, and we'll get 24.1124 kPa. In this class, we've gone over the advanced topic of flows with heat addition and friction, which is not usually presented in a compressible flow class for undergraduates, but it certainly is for graduate students. We briefly talked about the solution approach, and so using a numerical method with no other assumptions, we can account for friction and heat transfer in a variable area stream tube. We then discussed and showed how Prandtl number is related to these flows with particular Reynolds analogy. Prandtl number shows up in many other parts of fluid dynamics, in fact, in non-dimensional forms of the equations of motion. We then looked at isothermal flows where there's a static constant temperature through the flow and showed one particular example to find the pressure drop of an isothermal flow. Thank you very much for your time today. I'm Professor Steve Miller.